No, this will be 2 days. This will be 2 days. Just to give you the day to practice. We don't have a whole lot left to do, which is good. So we'll just take our time with it.
Just F and G.
F and G, yeah. And F is 8 items, 8 sections, and G is 6. Yeah, it's. We'll take our time with it though, because now's the time. We'll be seeing FRQs along the way, so it'll be good. Okay, so integrating by completing the square. After doing this time around, I actually think probably it would make sense to flip-flop these two that we just did, because yesterday we saw a little bit with arctan, and there's even an arctan in the homework assignment where you kind of have to do a U sub on, and that's kind of what ends up happening here with completing the square as well. So some of that arctan stuff from yesterday is going to kind of flow over into this. So we'll see how that all works. That's actually what example 1 is. But when we're doing completing the square, when you realize that that's the thing you need to do the integral that you have, you're going to end up with arcsine or arctan. And although it is a must-know antiderivative, arcsecant, for a variety of reasons, doesn't generally show up as something that you're going to have to like problem solve with. So really, we're just going to end up with the sine and tangent when we're doing these. So what is the must know for arcsine? What does that denominator look like? Right, root 1 minus x squared. It's got to be that way. If you have 1 over root 1 plus x squared, that is not, I don't think, something that we know how to take a derivative of, an antiderivative of, or I don't even know if it's 100% possible. So it's always going to be in that form, a number minus something squared. And then with arctan, what's the denominator have to be? 1 plus x squared. And the order of that does not matter. And the reason the order of that does not matter is because it's addition. And then, of course, arcsecant is the oddball. Since we're talking about them, we can drop it in. You're going to have that absolute value of x out front. And then you're going to have the square root that you had from sine, but reversed, so x squared minus 1. So again, I think the bulk, for a variety of reasons, the bulk of what you'll see with arcsecant is just recognizing that.
Good morning, teachers. Sorry for the interruption. Please look around your classroom and send any students that are not in dress code to the front of the auditorium at this time, including students not wearing a collar, students wearing a hoodie, or carrying a hoodie. Thank you.
But I wish they waited to period 2 to do this today. That would have been a good one because they did the 1-2 the other day. But anyway, back to where we're at. So those are our integrals. So let's take a look at some things where we kind of have to do a little bit of U sub to get our integrals to look like that. We haven't seen this. I don't think we've seen either of these yet. There are a lot of little things that can change here that you're going to have to deal with. And whether you're working with sine or tangent, the nuts and bolts of the way that they get dealt with kind of changes. Otherwise, we could just write some like 1 or 2 formulas. There are some people who teach these with just formulas. So the more you recognize them, the more you'll like see the pattern. But because they're just little differences between sine and tangent, I think it's better to just do them out. So that first integral looks a whole lot like the must know for arcsine, but it's not, right? What's wrong with that integral? Everything. There's a 4 there instead of 1. So especially with sine, what's going to happen when you have one of these is that thing's going to be a perfect square. And we'll see what happens there. The way we're going to solve this one is we are going to factor that 4 out of the expression underneath the square root bar. So I'm going to rewrite this as 1 over the square root of 4 times 1 minus, and if I divide, when I pull that 4 out, what does that x squared become? Correct, yeah, x squared over 4. And then, of course, a dx at the end. All right. So one of the things that's going to happen in these problems is we're going to end up in this situation where our constant, not our coefficient in front of the x like we've seen before, but our constant is just a is not 1, and we have to deal with that by factoring that constant out. Now, some algebra knowledge. You have the square root of two things being multiplied against each other. You are allowed to break that up into two separate square roots. So I have the square root of 4 times the square root of 1 minus x squared over 4 in my denominator, which means that I can make that square root of 4 a 2 and bring it out in front of the integral. I mean, I could have done this in like 3 more steps if I really wanted to, but I don't want to write 15 different things. So, and then this is really where the difference between tangent and sine is going to come into play, because you won't be taking a square root when you're doing this process with tangent, but because sine has the square root in it, you will be taking that square root here. So factor that number out, which does 2 things. It gives your x squared term a denominator of that number. And then when you're working in the sine case, that number now can be pulled all the way out to the front of the integral, but you then need to take its square root. Make sense? Okay. Algebra. That is algebra. So now we're ready to do u sub. We're doing u sub with arctan, arcsine. When we do that, the first thing we do is identify not u, but u squared, so we don't make a mistake with what exactly our u is and what our arguments are going to be. So what is my u squared in this problem? Disagree, because I can't take that thing's square root easily. I'm doing the u sub in my last integral. So what do I want in order to get, let me phrase this a different way. I want this to match, I want this integral, I don't care about the 1/2, that's a coefficient. I want this integral to match the must-know form. So where do I want that u squared? That's what my u squared equals. I want to have u squared instead of, where do I want to have u squared in this integral? Right, I want to replace the x squared over 4 with u squared, because then I have this must-know integral. It's just got a u there instead of an x. So u squared is my x squared over 4. Which means that u is x over 2, correct. That's why I said this will almost always be a square root, because that's the second time we've had to take a square root of 4 in this one. Which means that my du is 1/2 dx. And here's the part where I usually say, but I don't have a 1/2 dx. But I do have a 1/2 dx, right? My integral, with the way my integral is, I have the 1/2 out front, I have the dx out the back, so I actually have what I need here, and I don't have to make any adjustments. So these guys, when I go to rewrite with my u sub, those 2 things that I've highlighted in blue are completely being replaced with the du. So I have the integral of du, and then I just replace 1 over square root of 1 minus u squared. My color coding wasn't perfect here. I should have done the integral in black, so I could have done that, but we'll live. So yeah, so where did the 1/2 and the dx go? Well, that's what du equals. So putting du in there and multiplying it against everything else is as good as having a 1/2 coefficient out front and a dx out back. Where did my x squared go over 4? Sorry, I should be pointing to the right one. Where did my x squared over 4 go? It went right there with u squared. So our answer here, that is a must-know integral, and it is the arcsine of u. Yep. So our answer here is the arcsine of x over 2 plus c. Boom. So whenever you're doing an arcsine, that's what's always going to happen. The coefficient that you make doing the algebra is going to get eaten up with the calculus of u sub. Okay. So that's a new problem we haven't seen before. Another thing that can happen with inverse trig is a situation like this on the right-hand side. When you look at this, your first instinct should be to try some sort of u sub. If I set u equal to either x to the fourth or 1 plus x to the fourth, what's its derivative either way? Something with too many x's, 4x cubed, right? 1 or no 1, that doesn't matter. That'll just get washed out. X to the fourth has a derivative of 4x cubed. But then the other option that we have, specifically because of our inverse trig, is not to set u equal to x to the fourth, but u squared to x to the fourth. And that's what happens. So in this one, if u, and I'll do a better job color coding, if u squared is x to the fourth, what's u? X squared, yep. Which makes du 2x dx. Don't forget that dx. But I don't have 2x dx. I just have x dx. So I'll multiply by a half. Divide by 2, yeah. Divide by 2, multiply by a half. Same thing. Just what you choose to say. Which means that my x dx is going to be replaced with 1/2 du. So when I go to rewrite my integral, I have the integral of however you want to write it. Do you want to leave the 1 up the top and put the du down the bottom? Put the 1/2 out front. It doesn't. You could put the du on top. You could put the 1 on top. They're both okay. So I said however you want to write it. And now my denominator is 1 plus u squared. You're right. Yep. 1 plus u squared. Because x to the fourth is u squared. Boom. Which gives us 1/2 the arctan of u. Which means our answer plus c, of course, our answer is 1/2 the arctan of x squared. Yep. The places where you can kind of get tripped up is just the plus c. Thank you. Yep. Oh my God. How dare I? So yeah, the places where that can kind of get, where you can kind of get mixed up here is, you know, what goes in that spot. This is a u squared. It needs to be a u squared in order to put a u as your argument of arctan. So just follow what you're doing here. We replaced x to the fourth with u squared, and the must know is arctan of u, which we're then are going to replace back with x squared. So those little details can make things a little bit tricky. Okay, so that's kind of the lead-in for what we need to know in order to kind of do things with completing the square. So let's take a look at just kind of a reminder of how to complete the square. And don't miss the fact that I went from example 1 to example 4 in my notes there somehow. That was a big jump. I don't know what was going on there when I did this, but I haven't looked at this since last year. Okay, so sorry if you're watching the video because I'm playing with magnets on the board, but oh well. Yeah. Let's go. So, have you guys ever seen tiles like this before? Yeah, okay. Yes. All righty. So we use these to model things with quadratics. And when we have these models, we use this big blue square to represent x squared. And then these green rectangles are x by 1 rectangles. So the idea is that this guy is x by 1, making the little yellow guys 1, and the blue guy is an x by x square. So the blue represents your x squared, your green represents your x, and your yellow represents your little units. Our goal with completing the square is kind of twofold. We need to stay the same. I still need to be x squared plus 4x plus 8. That usually is our goal in math, is to not change things. That's how we end up with wrong answers. So we need to be equivalent to x squared plus 4x plus 8, but we want something to be a perfect square in there. So we want to also factor something so that when we factor it, it becomes x plus a number times x plus that exact same number. So that when we go to write it, instead of writing like x plus 3 times x minus 5, we can write it as x plus 3, the quantity squared. And then that's what's going to give us our must-know trigs in the end. So I have 1 blue tile, 4 green tiles, and 8 yellow tiles there. I have x squared plus 4x plus 8. It's called completing the square because I want to make a square out of the blue tile, all the green tiles, and then I can do not whatever I want, I've got to do the right thing, but either I need to add more yellow tiles or take some yellow tiles away. So we'll take a look at how that sort of works out. And the way that I do this, and you'll see this in the formulas, I need to take these green x's and I need to split them in half because I'm going to put half of the x's over here and half of the x's over here. And then I fill in the corner with either the yellow tiles I have, or I have to bring more yellow tiles into the picture. So that corner, to complete the square, needs 4 of my 8 yellow tiles. Okay. So according to my picture, here we go. According to my picture, this square that I have has dimensions that are x plus 1, 2, because if you go down the short side of these green rectangles, you're counting by ones. So it's an x plus 2 by x plus 2 squared. So our answer when we do the algebra is going to be x plus 2 squared, but that only accounts for 4 of the actual 8 yellow tiles I have. So we have to put a plus 4 at the end. We do, and I think hopefully I have them. I feel like there were 15 tiles last year. There's 8, and we're gonna be really close, but we'll get there. We'll draw little squares in if we have to. Some of them may have disappeared in the last 365 days. So yeah, so we've got x plus 2 squared plus 4. Where am I at? So that is equivalent. X plus 2 squared is 1x, 1x squared, 4 x's, and 4 units. So I need 4 more to give me the same thing plus 8. The method for doing this without magnet tiles on the board is you're going to add and subtract the same number to your equation. And that number is going to be b over 2, but squared. B as in, when we write polynomials, we consider the coefficients a, b, and c. So that's what I mean by that. So what you do here when you're writing this is you take and you do x squared plus 4x. You rewrite the first 2 terms. And then you take this b over 2 squared and you both add and subtract it to your polynomial. So in our case, b over 2 squared would be 4 over 2 squared, which is 4. So now what I'm going to do is I'm going to add it and then subtract it and then write my plus 8. So that is that is algebraically equivalent to the problem that we were given, right? X squared plus 4x. If I do that to a number and then I add 4 and subtract 4, I've done nothing to that number, and then I add 8. So x squared plus 4x is the same as x squared plus 4x, then plus 4, then minus 4, plus 8. For those of you guys that have Brogan, he used to like to say things like fancy form of 0. That's a fancy form of 0. Plus 4 minus 4. And then what we do is we take those first 3 and we factor them. So we take those first three and we factor them. We consider these three together, and they always factor the same. It's going to be x plus whatever you got in here before you squared, but squared. And then we take the last two and combine like terms. -4 plus 8 is +4. Which sure looks like what we did using our colored tiles. Back to the picture for a second. The two things we do right here in b over 2 squared are in that picture. Why do I take my b and divide by 2? Because I have to take the green and put an equal amount on the right and an equal amount on the bottom. That's why I did b over 2. Why did I square it? Because then I need to take and fill in this square at the bottom that just happens to be 2 by 2 because I designed it that way. So that's why it's b over 2 squared. It follows the picture. If this was 6x, I'd have a third green here, and now my yellows would be 3 by 3. So that's why it's b over 2 squared. Oh, cool. Questions on that one? Let's do a more fun one. That's the example that we're going to catch when we're doing arc tangent. Arc sine is always the trickier one because the way that you must know for arc sine, it's 1 minus x squared. So what's going to happen is the polynomial we're given is going to have an x squared term in it, but it's going to be negative. So whatever order it's given in, I wrote it this way, I think, to keep the first term positive. You got to get it in the normal form, and you got to factor that negative out, okay? So first step here is I'm going to rewrite, I'll do all the steps. You can combine these first two, but I'm going to rewrite it as -x squared plus 8x minus 15. And then I'm going to factor out that -1 to change all those signs to x squared minus 8x and plus 15. Algebra, right? I didn't do anything wrong. Moved terms around, good. Factored out a negative, changed everybody's sign. You could do that in one step. Maybe most times you won't even have to do this first step because it was already presented that way. Okay, so now all of the completing the square is happening inside of those parentheses. So the completing the square part of it, we'll do this. We'll x squared minus 8x, and now I've got to add and subtract b over 2 squared. So b over 2 squared, we'll write it off to the side since we're doing so many different things. It's 16 because it's -8 over 2, but squared. So the -8 didn't matter, but it'll come to play in the factoring. Gives us 16. So I need to write a plus 16 and then a minus 16. And then I've got to write my plus 15 from the problem. Fancy form of 0. I added 0 to the thing. I added 16 and then I took 16 away. I didn't do anything. Same steps as before, but I still have a negative and I'm still in parentheses. X squared minus 8x plus 16 is going to factor into x plus or minus whatever was there before you squared it. So this is going to be x minus 4, but squared. And then I've got to do minus 16 plus 15, which is -1. Okay. All right, close my parentheses out. I've done completing the square. For what we're going to have to do in our integrals, I don't want everything to be with the minus. I want to distribute that negative to those two terms. This is going to help us match to the must-know form. So when I distribute that negative out, I end up with negative the quantity x minus 4 squared plus 1. right, so I'm going to go the reverse way through these two integrals on the bottom. So I'm going to stick with the problem that we're working on, and then I'm going to come back and do the arctan one. Because that one actually is, I think, the trickier one. Okay. All right. So built into this next example as well is, how do I know I've got to do this technique to solve my integral? You had a card for that this morning. If you see a square root in the denominator and the thing inside it is quadratic, you'll probably have a 1 at the top. That kind of goes along with these two. So there is a u sub problem with something different at the top. But square root of something quadratic is a good sign that you have completing the square. But just watch out. Make sure you have just a constant in your numerator. Otherwise, you're not going to end up in the must-know form. So that's a really good sign. The negative x squared is a really good sign. The other thing is the same thing, constant in numerator with a quadratic denominator. So really it's that quadratic denominator in or out of a square root. The quadratic will never be able to be factored. That's not super important for AB because that's a separate technique. In BC, we would learn what to do with both forms. This, where it can't be factored, that's going to get us to arctan. This, where it can be factored, is a whole different technique that you'll either see in Calc 2. You will see in Calc 2 if you take it. But for this class, we won't see it. So that we won't have to select between those two, which is nice. But yeah, if you tried to factor this, it wouldn't work. If you use the quadratic formula on it, you would find out that this doesn't have any real roots. Same thing with this one here, but once you're underneath the square root, that's a pretty good sign. So that's what to look for when you do these ones. So your first step is to complete the square. We've got to get it. Basically, we have to do all the things we did right above here to make this integral, the integral of 1 over the square root of, and I'm going to just rewrite our answer up here so the 1 comes first and the minus comes second, because that really matches our must-know form. Our must-know form is 1 over the square root of 1 minus something squared. And that something is our u. Or I guess I should say, the way we normally do this is I usually define my u squared. My u squared is, which just makes u x minus 4. Which means, and my du is just dx, yeah. Backwards colors on this one, but that's okay. Which is nice. Anytime it's du equals dx, that's just a 1-for-1 swap. So when I go to rewrite my integral, I have the integral. I don't need to put a coefficient there like I normally do. My dx has become my du, and I just have 1 over square root of 1 minus u squared, which is a must-know. I should have made my u squared blue. That's a must-know, and that is arctan. Arctan of u plus c in blue, because I don't feel like moving my pen to the other side of the screen. Full disclosure. So then putting my u back in, I have the arctan of the arctan. Yes. Arctan of x minus 4 plus c. It really is just a horizontal shift. The argument just represented a horizontal shift, so it worked just like the must-know, but the argument didn't change x minus 4. Okay. The reason this example was easier was because we had the 1 there. When we go back across the page and do the next example, we're not going to have a 1 there. So we're going to have to put together what we're going to do with completing the square with what we did all the way up in the first example. So, okay, so from above, we know that this integral is equal to 1 over the square root of x plus 2 squared plus 4, which is not quite the must-know arctan formula. The problem is we've got a 4 there instead of a 1, and we've got to do algebra to get that to be a 1, which means we have to factor a 4 out of the denominator. We did it before with sine. Now we're doing it with tangent. We don't have to take any square roots this time around. So that'll be the major difference here. So I'm going to rewrite the integral, and I'll do it in 2 steps. So I'm going to do 4 times the quantity. What am I going to write if I've factored out a 4 from x plus 2 squared? Nope. I'm not going to do that because that doesn't follow algebra rules. The whole thing over 4, correct. Yep. X plus 2 squared over 4. I can't get my pen to change back to black. All right. X plus 2 but squared over 4, and then plus 1. Why? What? It's tangent. Yeah, no, I don't need to make it negative. So yeah, again, it's algebraically equivalent. If I distributed that 4 back in, I'd be back to where I started at. So it's algebraically equivalent. So now I'll bring the 1/4 out front. Like I said, you could do this in multiple steps, but I feel like there's so many steps here, I don't want to skip too much. X plus 2 squared over 4 plus 1 dx. And now I'm ready to do my u sub. But we're working with arcsine, arctan, so I'm going to identify my u squared so I don't make any mistakes. U squared is the thing that I want to just be u squared, x plus 2, but squared over 4. Take the square root of that, and I get u equals x plus 2 over 2. This time, Jack, if you wanted to do any algebra there, it would be correct to do. But with the squared there, you can't just divide things by 4. Yeah. Once there's an exponent there, that kind of kills doing that. Which makes my du this is where, yeah, looking at this, go ahead. It's 1/2 dx. Yep, 1/2 dx, yeah. Because what you really have here, when you have x plus 2 over 2, you have 1/2 x plus 1. So dividing it by 2 gives you x over 2, or 1/2 x, and then 2 divided by 2 is 1. So that's where the 1/2 dx comes from. But I don't have 1/2 dx. I have 1/4 dx, right? So this is where arctan is different. In arcsine, it just worked out. I had the thing I wanted. I don't have 1/2, I have 1/4. So what do I need to do? Yeah, divide by 2, right? Yeah. So in order to get this to match this, that's my question. I want my 1/2 dx to match 1/4 dx. I have to divide by 2, which means I'm going to multiply both sides by 1/2. So 1/2 of du equals 1/4 of dx, which is the thing that I have. Kranek. Sure thing. He's even getting up out of his seat already. Oh, no. All right, bye. Winter mantle. Real fast. Yeah. All right. Okay, so 1/2 du equals 1/4 dx. I've got the things that I need here. I can replace my 1/4 and my dx with a 1/2 and a du, which I'll do. I still have the integral. That integral is 1 over something. And that something is my u squared plus 1. And we are just about done. So that gives us arctan of u, 1/2 arctan of u, plus c. So we are 1/2 arctan of x plus 2 over 2, plus c. The major difference, and this will be our last example for today. I'll let you guys try a couple on your own. But the big difference between sine and tangent is whether you get a coefficient or not. With sine, you should never really get a coefficient when you're doing the fixing the fact that this isn't one thing. But with arctan, you'll always get a coefficient. So that's why, I mean, you could write formulas for these, but it's different for tan versus sine. So I think it's just better to figure it out so you get it right. All right, let's try some on our own.